This is me during the pandemic. Lost and insecure, you found me, lying on the floor, surrounded. With all the dire public health consequences of the once raging virus affecting our loved ones one by one, I felt like I could use what little I knew to investigate more about the spread of SARS-CoV-2, one way or another. But seriously, look at that magnificent beast. By now, it should be apparent that this is no ordinary academic presentation. There will be none of the usual rigor, stringency, or seriousness for that matter. What I'd like is to invite you to revisit the pandemic through the lens of a third world kid with a second-hand laptop trying his hand on first-rate technology. I'd like you to remember our running question. Is there a cheap way to model viral spread? Segue. One of the most controversial takes during the Philippines-style pandemic is the intentional limitation on the use of testing kits during the initial surges of infection. Of course, this was met with clarion calls for mass testing, if not targeted testing. Trace, test, isolate protocols were highly variable across different cities and municipalities. How was it handled at the time? That was certainly something. With 4.1 million cases, more than 65,000 deaths, and a middling 66.2% partial vaccination coverage, at least give the government props when an official actually urged the use of scientific methods in our pandemic response. 4 years into the pandemic and well into the 21st century, and we were just then entering the Renaissance era. So, what is my role here? With my little second-hand laptop that could, I produced freely shareable public interest research, factoids on the latest vaccines and their efficacy, disaster remote sensing, and being a general source of mild annoyance to the digital community. But perhaps the greatest opportunity I found as I learned how to do programming and remote sensing is how it's best applied in the public health sector. For more on this, you may watch some crash courses I made using different open source software packages following this link. In the meantime, allow me to share some of the results of my ongoing research on remotely sensed bioclimatic factors and communicable diseases. This is CONTAGION, Environmental Modeling for the Post-Pandemic Era. I'm your speaker for today, Jeremiah Feliciano, and let's get modeling. Before we proceed, some disclosures. I am a biologist by training and apparently needing retraining. I am also a data analyst for the Global Pool of Studies on the effect of COVID-19 on pregnancy. This is my presentation, an update to my undergraduate thesis 3 years ago, and will also be mostly packed with more jokes in a conference in June. To start with, let's look at the Philippines during the Delta surge. Around the same time as Delta began being the dominant strain in the Philippines, vaccinations against COVID-19 began rolling out to many identified vulnerable groups. On the other hand, to harmonize the policies in provincial areas with similar population profile, a new quarantine zone was made with a harmonic flourish by Filipino citizens. The NCR Plus is composed by the provinces mentioned in the TikTok video, which simply amounts to this region. I was interested by it because it is the best test case, now that we're hopefully in the post-COVID better normalcy. Vaccines are there, the policies are now marginally more coherent, and infections are rising, but with much better recovery rates. With this perfect storm, how can we use alternative means of monitoring COVID-19 spread from just using proxy factors? Simply put, what am I here for? I asked that same question and ended up with the two big questions. 1. Is there a cheap way to model the Delta COVID-19 surge in the NCR Plus? And if so, can I use satellite sense bioclimatic factors to do so? My data comes from the public domain, like the DOH COVID-19 cases dataset, or by using my primary methodology here, satellite remote sensing. Remote sensing is a rapidly developing technology that enables us to see many changes in the world using satellites or drones. The sensors of the instrument aboard the satellite is sensitive to electromagnetic waves. Once an electromagnetic wave reflected by the Earth's surface hits the sensor, the instrument will classify which band the wave belongs to. What's produced are called raster images. Depending on the satellite, there could be at least 4 raster images, one for each spectral band. For instance, Landsat 8 satellite can produce at least 8 raster images. It is from these data that we can use Geographic Information System software to create datasets for analysis. Now that we've got much of the brass tacks, here are our variables. Environmental factors including temperature, rainfall, and humidity. Atmospheric factors including nitrogen dioxide, sulfur dioxide, and carbon monoxide, and with an outcome measure of the monthly incidence of COVID-19 cases per locality in NCR+. I then use a mix of Google Earth Engine, QGIS software, and R language to power up these analytical models and see how sufficiently R factors associate with COVID-19 incidents through space and time. Perhaps let's answer first the second big question, so that there's a suspense buildup. I made some preliminary best subsets model selection to optimize the predictors that will yield the best explanatory model. I ended up with these variables. Out of the original set of predictors, only carbon monoxide was dropped since it poorly modeled the outcome and is the great mimic of the other variables. Now, one might ask, rightly, what does this mean for us? Some ideas. 1. The onset of meteorological disasters like typhoons during the monsoon season, which was particularly strong in 2021, may have triggered superspreader events, especially in low-lying, highly urban areas or steep rural localities, especially in evacuation centers. This explains the direct relationship between precipitation or temperature and COVID-19 cases. On the other hand, sulfur dioxide may have a weakly positive but still significant relationship because the industrial sector, which was just beginning to scale back to some normalcy in late 2021, is weakly caught by remotely sensed data. Lastly, NO2 positively correlates with incident cases since such data is highly associated with vehicular emissions, implying movement of persons. Relative humidity negatively correlates with COVID-19 cases just because the temperature is slowing down, and with it, the amount of vapor the atmosphere can hold. Just a climate thing. We said earlier that we're leaving out the first question for later. This is later. As a rule of thumb, simple associations can be elicited by ordinary linear regression. However, its explanatory power may be dampened simply by inappropriate modeling technique. So, how much of the data did our linear model with those quirky associations adequately explain? Only 38.6%. Definitely, we can do better. This is what the map looks like if we plug in the actual cases. That is the cases from June to December with the color, the intensity of the color matching the severity of the cases in that locality. We said earlier that we'll improve on the ordinary regression with time-weighted, geographically weighted, and geographically and temporally weighted regression. But let's see how the first time-weighted model fared. Not bad. The strength of the shade is proportional to the extent of new cases. In this case, the model below managed to capture some places more closely, particularly the National Capital Region, whose 17 localities together have the highest incidence, perhaps in the whole Philippines. Furthermore, we see that it is the most chronologically responsive in that the changes through time were more accounted for than the changes through space. which explains a subtle lack of variation between localities. With that said, its explanatory power shot up to 59.6%. Next, let's compare the observed cases with the geographically weighted model. In here, the weighting or the severity of the cases relates with the closeness or distance between localities. Now, the model is marginally better at capturing the closeness or distance between the number of cases between localities, as I said earlier, but then there seems to not be much of a change through time. Consequently, its explanatory power increased to 66.8%. Getting there. Lastly, let's see how our best of both worlds model compare with the observed cases. Not much, but it's honest work. Perhaps, we can more clearly appreciate which localities are predicted by the model to have just close enough cases that they practically color the same way. But we can better appreciate the spread through time. This geographically and temporally weighted model gets the average of both interspatial and intertemporal data points, resulting in a much more subdued and, dare I say, stable estimates of cases. Of course, there will be some outliers or rapid fluctuations, especially in mega cities or highly urbanized cities, which poses drastically more number of infected people. But that's to be expected because, as George Box, the American statistician, said, all models are wrong, but some are useful. Consequently, this model provided the highest explanatory power at 72.7%, far and away better than the ordinary regression we started with at 38.6%. Now that we know all this, why does it matter? The models provide a significant case study since the virus has waxed and waned, and the governmental and societal activities have ebbed and flowed with the virus. There have been tightening and loosening of movement restrictions and intensified vaccinations and other activities with a constant trade-off between health and economy in mind. However, some limitations do apply. Our remotely sensed data needs some ground truth data to further validate the accuracy of the measures. While each dataset has acceptable validation studies abroad, studies must overcome the validation hurdle to enable better adoption of the technology in the Philippines. Next, while we're confident that most cases in the registry may be somewhere between the Beta and Delta variants, there is no state routine genomic surveillance data that is publicly accessible. Furthermore, with regards to methodology, I advocate for narrower time intervals like weeks instead of months, and smaller geographical units like districts instead of localities. This has to do with how likely the size of the contiguous data that are being analyzed simultaneously could affect the real estimates of association being generated by the models. Imagine this as an exam for the whole batch where the perfect score of one student severely increases the average of the entire class. Lastly, the models are normative. They reasonably show how the dynamics of COVID-19 spread has changed, but they do not have predictive powers. So, we saw how environment and humans interact with the spread of the disease in simulations. But, how can we apply this in everyday life? First, avoid busy areas. Atmospheric pollutants follow vehicular emissions and you can snort pollutants. Avoid humans. Second, social distancing was and is a privilege. Think, why were cases rising in urban areas, maybe even urban shanty towns? While restrictions were eased, movement remains limited. In those infrequent movements, people may bring home the disease to other household members, disadvantaging high-density and low socioeconomic households. Lastly, be a kind physician to your current friends, future colleagues, and patients. We have to spread the culture of care even amongst ourselves, and we are some of the hardest people to care for ourselves, much more for children. So, here are my references. And here are some contact information. You can also contact me via OG Abort if you're interested. And that's basically it. This has been Contagion, surveilling COVID-19 spread through modeling and simulations.